to class this fine morning. So let's see. Last time we were talking about. Let's see who else with us in the chat. Looks like Hank's there, Farden, Mr. Ivy, Mr. Hargraves. Excellent. Last time we were talking about the different unit systems for measuring large quantities of data. So just to kind of recap, right? How many bits are in a nibble? 4. How many bits are in a byte? 8. The nibble is a useful quantity because one nibble is exactly 1 hexadecimal character. And so that's, I'll say nibbles quite a bit. All right, so 8 bits is a byte. And then once you've got a byte, depending on which system you're using, either the metric prefixes for powers of 1,000 of bytes or bits, or the power of 2 system where you go up by powers of 1024 each time. But the part that's frustrating there is that if you see kilobyte, you can't necessarily assume that it's 1,000 bytes. It might be 1024. And you just have to pay attention to the context or what you're looking at, right? Now, 20 years from now, we may be totally standardized and everybody would say, all right, kilobyte will always be 1,000 bytes. And if I want to talk about 1024 bytes, I would say kibibyte rather than kilobyte. That is, it's not universal, at least not now. So just be on the lookout for that. I'm kind of old school, so I still kind of mentally think of this in the 1024 system, but that's just because back in my day, that's how it was. So anyway, okay, so we're going to kind of move into how do we, so we've talked about, sort of individual low-level logic gates. And then we said, okay, if you put lots and lots of these together, you'd have large quantities of bits, ones and zeros. We need a way to like count that, and that's sort of what we did last time. And then also the hexadecimal to sort of notate it in a more compact way than just a bunch of ones and zeros. So then the other question that we want to do is, or start talking about, and this will take us a couple weeks probably, is how do you store information in ones and zeros, right? So if everything to a computer in the circuitry is just really a bunch of ones and zeros, how do we store numbers? How do we store text? How do we store videos, right? Like all of that stuff, if it's ultimately ones and zeros, we have to encode that data, whatever it is, in terms of the bit patterns, okay? And so what is the standard, or what are the standards for encoding different kinds of information? We'll start with numerical information because, well, that maybe is the most natural place to start on a computer, but we'll also talk about text and then maybe go a little bit into things like pictures and video and such. Okay, so we'll start with sort of numerical data. And there are really 2 kinds of numerical data, and we'll treat them separately, and we'll start with one of them, which is you can talk about whole numbers, possibly positive or negative. Okay, so 8, 7, 32, 4,000, right? Things like that, or possibly also negatives. So integer storage is where we'll start. And then we could also talk about decimal stuff. So how would you store 3.14 on a computer? So that's called floating point. And that's a lot more complicated, the system for encoding it. So we'll get there. But we'll start today, and this will probably take us at least the rest of this week, maybe a little bit next week, to talk about just integer storage. Okay. So for the sake of demonstration for all of this, we're going to do everything with just 8 bits. So that will feel a little bit artificially limiting, and it will limit the sizes of the numbers that we're able to encode. The good news is that to do all of this stuff with 32 bits, it'll all work exactly the same way, except there's just more bits. That's it. Okay, so 8 bits is sort of enough for doing on pencil and paper, and then how you scale this up to more bits is basically the same thing. It's just more bits. Okay. All right. So to sort of recap, what did we do when we did hexadecimal? Okay. So if I wrote down this bit pattern, 0B1111. Okay. So the bit pattern is 1111. What is that in hex? Okay, it's F in hex. Okay, how did I know it was F other than just memorizing the table? Right, okay, so what I did was we said, all right, let me take 1111 and I'm going to decode that by understanding each of the positions as having a place value, and they go up by factors of 2 each time here, unlike, in third grade, they went up by factors of 10 because you were doing base 10 stuff. Here, we're doing base 2 stuff. And so you said, okay, this is a 1 plus a 2 plus a 4 plus an 8, which is 15, or F in hexadecimal. Okay, so the same sort of thing will be going on here, that we'll think of the place values of each bit as going up by factors of 2 each time. Okay, here I only used 4 bits, so if I scale this up to 8 bits, then what are my place values going to be? I'll still have 1, 2, 4, and 8, or actually I should, from your perspective, 1, 2, 4, and 8. But then I'm going to have 4 more, and what are their place values going to be? What'll be after 8? How did I go from 1 to 2, 2 to 4, 4 to 8, and so on? Okay, 16, then 32, then, and then finally 128. Okay, so so the distinction, well, 2 things I'd like to note here. This, notice what I wrote there. Kind of like, how do I know, or how do you know that something is meant to be interpreted as hex? Well, often we put 0x in front of it, or just, the word hexadecimal or something. Okay, but typically you see in symbols, right, you'd see 0x something or another, and that would tell you, oh, whatever's after the X is something in hexadecimal. Well, similarly, how could I tell you that you have something in binary? Well, 0B, blah, 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 okay, is a common way that you see this on machines. And I'll try and stick with that as much as possible. Okay. So there are 2 different kinds. So let's see, we want to talk about integer storage. There are 2 kinds of integers. Okay. We could talk about unsigned integers, where we don't care about allowing numbers to be either positive or negative. Okay, so if we're just assuming that whatever kind of numbers we're tracking can only be positive quantities, then an unsigned integer is an appropriate data type for that. Okay. In practice, and I guess there are situations where you want to use these. A good example would be like the play counter on YouTube. They actually do use signed integers for that, but which we'll talk about why later. But you could say, oh, well, why would I ever need to talk about a negative number of count plays, right? That doesn't make sense. It would make sense, though, if you said, all right, well, let's say that, so-and-so's music video has 1 million views, but then you find out that 50,000 of them were really from bots, and YouTube is like, I'm not paying you ad revenue on bots because bots don't click ads. So I'm going to take those 50,000 away from you, right? Well, in order to do subtraction, you need to have signed integers. Okay, but mathematically, at least, we can certainly talk about this. So you can have an unsigned integer where you don't include any negatives. Okay, so let's talk about how to do this with 8 bits. What is the range of things we can encode? Okay, so the data type that we'll call this is a uint8. U for unsigned, int for integer, and 8 for the number of bits that we're going to encode it with. Okay, so that's sort of the type, the object type that we have. So what's the range of numbers that we could encode with this? Well, how many things can we encode with 8 bits? Okay, how many different patterns are there? Yeah. So with 1 bit, there's 2, right? So with 8 bits, how many different things can we encode? 256. We can, okay, so you're right, but you're wrong. Okay, so we can encode 256 different things. However, if we want to encode numbers, integers, where do we start? 0. And so what's the biggest one we can encode? 255, because that's a total of 256 things. Okay, we can encode here 2 to the 8th. We can encode 2 to the 8th different patterns, right? So the number of things you can encode with a particular number of bits is 2 to that number, right? And the reason is, how many choices do you have for a single bit? 2, okay? How many do you have for the next bit? 2. How many do you have for the bit after that? It's 2 for every single bit position that you have. Okay, so there's that. But does your choice of 1 bit position or 1 bit influence what the next bit is? No, they have nothing whatsoever to do with each other. Okay, so those are independent choices, and in probability, the number of ways of doing something, if there's, I mean, think of it this way, right? If you've got 5 different t-shirts and 6 different pairs of jeans, how many outfit combinations do you have that you could pick? Well, it'd be 30, right? You could, for each pair of jeans, you could wear any of the 5 t-shirts, and similarly, right? So it multiplies. It's just that in this case, everything is a choice of 2, right? So it'd be like you got 2 pairs of jeans, you got 2 shirts, you got 2 different pairs of shoes, you got 2 hats, you've got 2 handbags. I don't know, right? Uh, Maybe handbags is not the best example around here. And why is it men don't carry purses? That would be kind of useful, wouldn't they? Anyway, okay. Question? No? Okay, so point being, you have 2 choices for each bit, and so because those are all independent, the number of ways just multiplies, and 2 to the 8th is, of course, the compact way to write that. Okay, so 2 to the 8th different patterns, i.e. 256 patterns, okay? And so we can encode 256 things. Well, we need to encode 0. Through, I hate English. through, tough. I really hate the word Tuesday or guarantee. There's some words in English I really just do not like having to spell. All right, so if we can do 256 different patterns and we need to start with 0, then that means the biggest number we can encode is 255 as an unsigned integer, okay? Right, okay. And the pattern for how to do this is exactly what we've seen. You just start with the place value, okay? So, for example, let's just make up a bit pattern. Ethan, give me a bit pattern, 8 bits. Just make something up. Okay, thank you. All right, so let's say that we have this in binary, and just so we're clear, what is that in hex? This would be D, not C, sorry, it's too early. Okay, and then the other one is 6. Okay, so let me make that D more DE. There we go. Okay, all right, so in hex it's D6, right? All right, what is this as an unsigned integer? Well, there's a couple ways I can actually do this computation. The first would be, let me start writing my different place values, okay? And if I've got 8 positions, then I don't need to go any further than this one, okay? And then just write your bits down below it. Okay, and those are whatever Ethan gave me. Okay, and then just add it up, right? So I've got 128 plus 64 plus 16 plus 4 plus 2. Well, what is that? Well, 128 plus 164 is 192, plus 16 would be 202, 208, plus 4 is 212, plus 2 is 214. Does that check out? Did I? Yeah, well, 202 plus the 6 is 208. Plus 4 would be 212. Plus 2 would be 216 or 214. Yeah, okay. Yeah, I suck at arithmetic, period, but especially early in the morning. Okay, but 214. Now, there's another way to do this, which I'll show you in just a second, but for now, does that make sense, right? All I did is I put the bits in their proper positions, and then the place values go up by 2 each time. Unlike, of course, in regular arithmetic, like in grade school, what were they? 1, 10, 100, and so on, right? So we're doing things just like we did in grade school, except it's as if I cut off 8 of your fingers. Okay? Which, yeah. Okay, so 214, you guys agree? Yeah? All right, what's the other way that I could have come up with 214? Besides kind of going through this place value system. The other way I could have done it was actually to look at the hex. All right, because in hexadecimal, how do the place values increase? They go up by powers of, or factors of 16, right? So here I have a 6 in the ones place, and the D is in the what's place? The 16's place, okay? So I have 6 plus, well, D counts as what number? 13, and it's in the 16's place. So this would be 13 times 16 plus 6. okay, D for the 13, and then 6 is obviously just 6, okay? And then if we go through and multiply this out, is in fact 13 times 16 plus 6, 214? Well, let's just make sure that I'm not being a complete idiot this morning. Sure enough, it's 214. Okay, so that's the other way that you can do this, is if you've got it in hex, then you can skip the binary, okay? But importantly, I'd like you guys to be able to do both, right? So there's really, 3 systems that we'll have to be fluent in. Hex, binary, those are what we're learning new. And then of course, base 10, you guys learned, your entire life. Okay, okay, good. Question, preguntas, Fragen? No? Okay. Yes, Mr. Runge. I'm sorry? Because in hexadecimal, how many different digits do you have? You got 0 through 9, that's 10 of them. And then A, B, C, D, E, and F gives you another 6, right? So you have a total of 16 digits, and I'm air quoting on digit there. And so that means that the system is a base 16 system. Okay, so base 10, you go up by powers of 10. Base 2, you go up by powers of 2. Base 16, you go up by powers of 16. Okay, so that's why. Okay. Yeah. So what would be the next position if I had another hex character? What would be the next place value? It'd be 16 squared, which happens to be 256, right? So the place values in hexadecimal would be the 1's place, the 16's place, the next one would be 16 squared, 16 cubed, and so on. Yes? Okay. So let me actually not think about it that I started with 128. Let me think about it that I started with 1 on the other end, and then I had 8-bit positions, and if I double each time, the very last one is 128. I don't hit 256 because that would be a 9th bit. Okay, now you might look at this and say, wait a minute, Dr. C, you told me that I can encode everything up to 255. So why isn't there a 256 there? But because there doesn't need to be, right? So what would 255 be in if we encode it in binary? Everything would be a 1, right? A 128 plus a 64 plus a 32 plus a 16 plus an 8 plus a 4 plus a 2 plus a 1, that's all 255. That's the largest thing you can encode as an unsigned integer with 8 bits. Okay, what would that correspond to in hexadecimal, by the way? All 1's would be FF, exactly. Okay, is that okay? Yeah, and this will sink in, right? Essentially what you guys are gonna have to do is you're relearning grade school arithmetic for a different base. Now there will be one other minor complication. It's actually a major complication. We'll talk about that next time, which is, well, like let's take the number 255, just for sake of example. Okay, you got 255, great. You got 255 Snickers bars. I give you 5 more Snickers bars. How many Snickers bars do you have? You'd say, oh, I got 260 Snickers bars. No big deal. Can you express 260 in 8 bits? No. Okay, so in a computer, this is called overflow, and it's a problem. In grade school arithmetic, if you just need to write more digits, you just do it. Okay, but on the computer, we don't have that luxury. So that will be the source of some major irritation later, but we'll get there. Okay, so, right, that's how we deal with unsigned integers, okay? Now, we can do this process in reverse, so Who do I want to pick on? Mr. Borden, can you give me a number that's between 0 and 255? A whole number, please, an integer. Okay. Okay, and I'm going to write a subscript of 10 here so that we don't get confused and think that that we're writing something in hex. Okay, so Cole picked the number 47, okay, meaning 4 10s and a 7, right? Normal grade school arithmetic, not 4 7 in hex. And Coy did the 16, Coy's online. The 16, where did that come from again? I think I answered that question a second ago. It's because in hexadecimal, you're going up by factors of 16 each time. Okay, so how would I write this thing in binary and therefore hex? Well, let me start by writing out my place value. And I may not need all of these positions, but I'm going to go ahead and force myself to use 8 bits here for sake of demonstration. All right, so all I've done is I've written out all of the place values, the 8 positions worth of place value. Good? We know. Okay, now I've got the number 47. Does 47 fit into 128? Or sorry, let me say that the other way. Does 128 fit into 47? No. Does 64 fit into 120 or to 47? No. Does 32 fit into 47? Yes, once. Okay, so I didn't use this one. I didn't use that one. I did use the 32. How much is left over? 15, right? 47 minus 32 is 15, I think. Yes? Okay. All right, so then we just continue the process. Does 16 go into 15? No. Does 8 go into 15? Yes. Once. How much is left over? 7. Does 4 go into 7? Yep, once. How much is left over? 3. Does 2 go into 3? Yes. How much is left over? 1. And then at this point, then we're there. Okay, so this is how you go the other direction, meaning from a, so on the previous sheet, slide, whatever, we took a binary number and we decoded it and figured out what it was representing. Here we've done the opposite. We've taken a decoded number, a base 10 number that we just pulled out of thin air, and we figured out how to encode it with, in this case, 8 bits. Okay. Now, did we really need all 8 bits here? No, right? 6 bits would have been sufficient, okay? But the so while in arithmetic, like grade school arithmetic, like let's say you wrote down the number 047, right? That is 47, right? But would you ever write 047 on paper? Probably not. There's not really a good reason to include that leading 0 that doesn't do anything for you. Okay. However, on the computer, and this is really important, everything is going to get stored ultimately in 8-bit chunks. Okay, so if you don't need but 6 of those 8 bits, those other 2 bits are still there. And so what's the only thing that you could reasonably set them to? Zeros, but they're still there, right? Unlike, you know, writing 047 on paper versus 47 on paper, right? We're not trying to encode this stuff for the purposes of humans. We're trying to encode this stuff for the purposes of machine, and those are not the same thing, sadly. Okay, so this would be the binary pattern, and then while we're at it then, what would this be in hexadecimal? Okay, so 47 in base 10, we just figured out is that in binary, and so as a hexadecimal number, what is it? 2F, yes. Okay. And then, of course, we could, do this process in reverse to check that we, in fact, have the correct number, like we did on the other side. Okay, is that okay? Okay, so the unsigned stuff is pretty easy. It works just the way it does in grade school arithmetic, except that we're going up by powers of 2 or 16 if we're doing hex. Right. Signed integers are going to be much more fun. Okay, so let me kind of pause for a moment and see if we've got any questions from online. Okay, Coy says he's good. Everybody in the room, what questions do you have? We're not all fully awake yet. See, especially you freshmen have not discovered the joyous substance that is coffee. No, Mr. Runge, are you not a coffee drinker? What do you like? Red Bull? Tea? With what? Nothing. Oh. We'll see how long that ship lasts before it sails. Huh? Oh, yeah. Well, yeah. If you do a line of cocaine every morning, then you're going to be wide awake. But don't recommend that. Yeah, that's all right. Okay, so I'm going to pause for the moment, and I'm going to show you something in base 10. So we'll go back to grade school arithmetic, okay? And I'm going to show you something that's probably going to blow your minds at first, okay? Which is a really clever way to do subtraction. Okay, so this is going to be way more mind-blowing than, say, how many of you guys know the nines trick for multiplication? Right, with your fingers, right? Okay, how many of you have never heard of that before? The nines trick? You never heard of the nines trick? Okay, you want to multiply, let's say 4 by 9. Okay, got my 10 fingers out. All right, so 4 times 9, I'm going to put down my fourth finger. Well, there are 3 and 6. 4 times 9 is 36. Yeah, isn't that kind of clever? Obviously, it only works with 9. It also only works if you've got 10 fingers, but yeah, anyway. Okay, so let me do a really sneaky subtraction trick. All right, so let's take 47, just because Cole picked it, and let's subtract 32. And of course, what's the answer? 15. Okay, but how did you get that? Well, you said 2 from 7 is 5, 3 from 4 is 1, and that's it. I didn't have to do any borrowing in this particular example, but if I change the numbers, I might have to. All right, let me take the number 32. Okay, and what I'm going to do is I'm going to pair off all of the digits. Okay, so I'm going to pair, there are 10 digits, right? So that means I could pair all of them and have 5 such pairs. And the way I choose to pair them is I'm going to pair 0 with 9, 1 with 8, 2 with 7, 3 with 6, 4 with 5. Good? Okay, so what does 3 pair with? 3 pairs with 6, and 2 pairs with 7, right? Okay, so I'm going to change 32 into 67. Okay, all I did was I replaced each of its digits with its paired digit. Okay, now you might say, why, Dr. McKinney? Don't ask that yet. Okay, just trust me. I'm a doctor. Okay, the other thing I'm going to do is I'm going to add 1. And I get 6, 8. Good? Okay, now let me take the number that I started with, 47, and let me take 68, and let's add those two numbers. Okay, what's 7 plus 8? 15, so 5 carry a 1. What is 4 plus 6 plus 1? 11, so 1 carry a 1, and then just ignore that carry that went past the second digit position. So what do I get? Huh! That's exactly what I get when I did it the other way. You guys can't see my like rapturous smile under my mask here. Like, isn't that like the most amazing thing ever? Huh? You're not following how this works? No? Okay, it is kind of magic, right? All right, well, let's pick a 3-digit number, Evan. Just any 3-digit number you want. Hmm? 127. Mr. Runge, pick another 2-digit number. Something smaller than 127, please. Huh? 63. Okay. So you guys are picking the numbers, not me, right? Okay, so this means that it's a legitimate magic trick, not a, right, I'm cherry picking the numbers. All right, so let me take 63. What does 6 pair with? 3, and what does 3 pair with? 6. Okay, so this happens to just reverse, but that's just because of the numbers you picked. And then I'm going to add 1 to that, and I'm going to get 37. Okay, so what's the answer that we should get if we do this correctly? 3 from 7 is 4. 6 from 12. Well, what would I have to do? I'd have to borrow and carry, and I've got 12 minus 6 is 6. So we should expect 64 as our answer. Okay? Good? Just if we did this the regular way. All right, so 37 is my magic number. So I'm going to take 127 was the number, the first number, and then I've got 37, and I'm going to add them. Okay, what's 7 plus 7? 4, carry a 1. What's 1 plus 2 plus 3? 6. Oh, okay. I'm sorry, Evan. We need to do this again. I needed a 3-digit number that was smaller than 127. Okay. So, sorry. So let's start over. Because otherwise the magic trick is not quite right. All right, so we had 127. Pick a 3-digit number. 112, okay. So we'd get 15 is what we're expecting, okay? All right, so 112, what are the pairs for all of the digits? 1 paired with 9, 9, and 8. Yes? Okay, and then I'm going to add 1 to that. So in this case, I get 999. Okay, so I'm going to take 127 and 999, and I'm going to add these, but I'm going to throw away anything that would carry into the 4th digit. I have 3 digits so far, right? Okay, so I'm going to do addition and carry as necessary, but anything that would carry into the 4th digit, throw it away. Okay? All right, so 7 plus 9 is? Okay, wait a minute. What did I screw up here? The pairs are wrong. What is 1 pair with? 8. 0 pairs with 9. Okay. Trust me, this is way easier in binary because guess what 0 pairs with? What else is there? Right? Okay. All right. So sorry. So then I'm going to add 1, and what did I get? I got 888. Okay. I'm not being a very good magician today because I keep messing up my trick. Right? I wouldn't last 10 seconds on Penn and Teller. All right. So 888. Okay. So I'm going to add those. 7 and 8 is 5, carry a 1. 8 and 2 and 1 is 1, carry a 1. 8, 1 and 1 is 0, carry a 1. And what did I say? Ignore anything that carries past the third digit. Why past the third digit? Because I started with 3-digit numbers. Okay. Now, if we go back to, and I'll do the original magic trick with, what was the number, Mr. Runge, what was the number you picked before I screwed this all up? Yeah, 63, right? So what I should have done was write it as 063, and then this would work, okay? So we'll do that in a moment. But what do I get? 15. Wow. Huh? Wow. How many of you guys have ever seen this before? Yeah, there's probably a good reason we don't teach this in elementary school, right? Um, you know, it's hard enough to get first graders to do regular subtraction, much less this voodoo. Okay, but here's what the voodoo is really up to. I had a problem to do subtraction. I did all this magic stuff, but notice in all of the magic, did I ever do subtraction? Never. What I did was I turned the problem into addition. Yeah? One could argue that addition is easier than subtraction. Okay, but I recast the problem in terms of addition instead of in terms of subtraction. And then the magic trick was this sort of pairing of numbers thing. Okay, all right, let's do the other example which we had, which is 127 and 63. So let me go on to a new sheet here. All right, 127 minus 63, and I'm going to be correct this time and think of it as 063. Okay, for the stuff that you did in elementary school, it doesn't matter, right? Because what do we get? 4, and then a 6, and that's it. Done. 064. Okay. Okay, so that part's okay. All right, so what's the magic trick? Well, what is 63? Let's take that. What did 6 pair with? Okay, 6 paired with 0 and 9, 1 and 8, 2 and 7, 3 and 6 pair, right? So the paired version of 63 is 36, to which I'm going to add 1 to get 37. Yes. Oh, damn it. That's what I messed up the last time. Okay, thank you. Students and being correct. Oops. Okay, I put the line in the wrong spot. There we go. Okay, what did 0 pair with? He pairs with 9. Okay, so the number 63, his sort of magic pair with 3 digits is 937. Gucci? Okay, take 127 and 937 and add them. Okay, so 127 and 937. And remember, anything that goes beyond the third digit, because I started with 3-digit numbers, just toss it. Okay, so I'd have 7 and 7 is 14. Add, that's 6. 9 and 1 is 0. There would be a carry, but I'm going to toss anything that carries past the third digit. Why past the third digit? Because we started with 3-digit numbers. Okay, and we get 64. which was what we were supposed to get. Yeah? Isn't this, I mean, it is kind of magic, right? All right, do I have any future math majors in the class? No? None of you? Okay, yeah, close enough. Your assignment for next time is to figure out why this works. No, kidding. It's kind of, yeah. We could prove why this always works, right? But a good magician never reveals his secrets, so I'll skip that. Okay, so why am I doing this? Not just to show you some really cool arithmetic trick, but it turns out that this approach is precisely the approach that we want to do in the binary world, and it really pays dividends there. Okay, so so I wanted to show you this in base 10 first to kind of familiarize ourselves with the game, and then when we do this in binary, it won't be quite as horrible. Okay, now one part about doing this in binary will be much easier than it is here, namely, how do the digits pair? 0 pairs with 1 and 1 pairs with 0, right? There's only 2 digits, so it's really easy. Unlike in base 10, where we had to kind of think, all right, well, what does 1 pair with again? 8, 9, and as you saw, I screwed it up a couple of times. Okay, so this technique is called 9's complement, and then what we're going to do, or 10's complement actually, what we're going to do next time is talk about 2's complement, which is how you do this in the binary world. Okay. Okay. Questions, preguntas, fragen. 9? No? All right. Well, we'll pick up with this on Friday. All right. We'll cut the stream and see you guys later. Don't forget to like and subscribe. See you later.